Hello everyone, myself Dr. Santavigundu. I welcome you all to this lecture of soft computing techniques. This is the first lecture of module 8. So we have seen in module 7 the definitions and basic approach of multi-objective optimizations. We also solve one multi-objective optimization problem by using genetic algorithm, that is VEGA method. Today we learn few more definitions and applications. So first one is that vector optimized evolution strategy or VOES. So VOES is a type of evolutionary optimization algorithm that uses a vectorized approach to optimize problems. It is a variant of the evolution strategy algorithm, which is a popular optimization technique inspired by the process of natural evolution. Key features: vector optimizations. VOEs optimize a vector of parameters simultaneously rather than optimizing individual parameters sequentially. Evolutionary approach. VOEs uses an evolutionary approach where a population of candidate solution is evolved and over time through mutation, selection, and recombination. Adaptive step size control. VOS uses an adaptive step size control mechanism to adjust the step size of the optimization process based on the performance of the populations. Multi-objective optimization. VOS can be used for multi-objective optimization problems where multiple conflicting objectives need to be optimized simultaneously. Algorithms. First one is that initialization. Initialize a population of candidate solutions where each solution is a vector of parameters. Evaluation. Evaluate the fitness of each solution in the population using a fitness function. Selection. Select a subset of the population based on their fitness values. Recombination. Apply the recombination or crossover to the offspring solutions to create new solutions. Mutation. Apply mutation to the selected solutions to create new mutated offsprings. Step size control. Adjust the step size of the optimization process based on the performance of the populations. Repeat the steps 2 to 6 until a termination criteria is met. Now try to understand one example. Suppose we are having that one minimizing problems. Minimize f1x equal to something like x square. You can write minimize f2x equal to something like x minus 2 whole square. Keep it minus, so that is basically maximum f2x. So here initial first to said the initial populations you need to fix in size of initial population size, then the number of iterations, then you can find the crossover probability, iterations, mutation probability. Suppose here the population size, suppose x belongs to some interval, let x belongs to the interval, you can write it 1 to 10 or something 0 to 10. So initial population size may be 5, number of iterations need, let's 50, crossover probability, let's say it is something like 0.7, mutation very less, like it is 0.1. So this is a vector. So after a certain stage, we will get the our result. So this is known as the VOES. Okay. So suppose after the iteration iteration initially, okay, after iteration 10, we'll get the result something like f1x maybe something like 1.25 or something like that. X2 maybe something like 0.5 like that. After 15 we'll get something like we'll get the output. So that is basically the VOS. Now advantage. It's improved the convergence. VOS can converge faster than traditional ES algorithm due to its vectorized approach. Better exploration, VOS can explore the search space more efficiently due to its adaptive step size control mechanism. Multi-objective optimization, VOS can handle multi-objective optimization problems, which is useful in many real-world applications. So applications, optimization of complex systems, VOES can be used to optimize complex systems such as chemical processes, financial portfolios, and machine learning models. VOES can be used to solve multi-objective optimization problems such as optimizing the performance of a system while minimizing its cost. Machine learning, VOES can be used to optimize machine learning models such as neural networks to improve their performance and generalizability. Next one is that weight-based genetic algorithm, WBGA. A weight-based genetic algorithm, WBGA, is a variant of the traditional genetic algorithm designed for multi-objective optimization problems. In multi-objective optimization, we typically have conflicting objectives, and the goal is to find a set of solutions that represents the Pareto fund, which is the set of non-dominated solutions. WBGA works by assigning a weight to each objective functions and combines these weighted objective into a single scalar objective functions. This allows the genetic algorithm to work with multiple objectives simultaneously by reducing them to a single objective. Key concepts in WBGA. First one is that multi-objective optimizations. In multi-objective optimization, there are multiple often conflicting objectives that need to be optimized simultaneously. For example, in an engineering design problems, we want to minimize both cost and weights, but these two objectives are often in conflict. Scalarization. WBGA transforms a multi-objective optimization problems into a single objective problem using a scalarization functions. The most common method is to compute a weighted sum of the objectives. Now weighted sum. In WBGA, the weighted sum of all objectives is used as a single scalar value, that is fx equal to w1 f1x plus w2 f2x and so on up to wm fmx, where fx is the scalarized objective functions, fix is the value of the ith objective function at solution x, wi is the weight associated with the ith objective. The weights w1, w2, wm determine the relative importance of each objective, and here summation of the weights, that is summation of I equal to 1 to m, wi equal to 1. Steps in WBG. First one is that initialization. Initialize a population of potential solutions. Each individual represents a solution to the multi-objective problem. Objective evaluation. Evaluate each individual with respect to all objective functions. Scalarization. Compute the scalarized objective function, that is fx, for each individual using the weighted sum. Selection. Select individual for reproduction based on the scalarized objective function values. Crossover and mutation. Perform genetic operations such as crossover and mutation to the selected individual to generate new solutions. Replacement. Replace the old population with the new generation, ensuring that the base solutions are carried forward. Termination. Repeat the process until the stopping criteria are met, that is the certain number of generations, a convergence to a Pareto fund, etc. Now try to understand one numerical example. We'll solve one question by the method of WBGA. So consider a simple two objective optimization problem with the following objectives. Objective 1 is that minimize f1x equal to x square. Object 2 is that you can write it maximize f2x equal to x minus 3 whole square or minimize f2x equal to x minus 3 whole square. We'll solve this problem using WBGA, where we assign weights to the two objectives and combining them into a single objective. So initialize the populations. So we consider the following 5 individuals, that is at individual 1, 2, 3, 4, 5, 6. So at individual 1 x equal to 1, individual 2 x equal to 2, individual 3 x equal to 3, individual 4 is x equal to 4, and at 5 x equal to 5. Objective evaluation. Now we calculate the objective for each individual. So you know that f1x equal to x square. So 1 square you will get 1, 2 square you will get 4, 3 square you will get 9, and similarly 16, 14. Here it is, if f21 is equal to minus of 1 minus 3 whole square, so that is minus 4. Similarly you will get it for 2 minus 1, then 0, then minus 1, then 4. Next is that assign weights and scalarization. So we'll assume that W1 equal to 0.5. So that is the weight for F1x. Weight for F1x. W2 equal to 0.5. That is the weight for F2x. So here you have seen that W1 plus W2 equal to 1. So here scalarized value Fx is equal to 0.5 into f1x plus 0.5 into f2x, which is equal to 0.5 into x square plus 0.5 into minus of x minus 3 whole square. So at x equal to 1, so that is 0.5 into 1 into 0.5 into minus 4, so that is 0.5 minus 2, that is minus 1.5. So selections. So we now perform selection based on the scalarized objective function values fx. In this case, we select individual with the best fx values. As we are minimizing the scalarized objective, so the selected individual will be the ones with the lowest fx values. From the table above, we see that the individual with x equal to 1 has the lowest fx, so it is selected. So basically, we are using here tournament selections. We are using a tournament selection method. Then crossover and mutation. Next, we apply crossover and mutation to generate new offspring. Assume we perform simple crossover and mutation on selected individual. So crossover, combine the solution as for example, take x equal to 1 and x equal to 2 to create a new individual. Mutation introduces small random changes to individual to explore in the search space. So after applying crossover and mutation, we might get the following new individuals. So at individual 6, x equal to 1.5, 7, 2.5, 8, 3.5, 9, 4.5, at 10 it is 5.5. Next is we need to the re-evolution and replacement. So after the crossover and mutation steps, we re-evaluate the new population based on the scalarized objective functions and replace the old population with the new generation. This process repeats for a set number of generations or until convergence. Step 7, termination. The algorithm stops once a termination condition is met, that is after a set number of generations or when the population has converged to a set of non-dominated solutions. Now summary of WBGA. So weighted sum approach WBGA uses a weighted sum objective to convert the multi-objective problems into a single objective one. The selection based on the scalarized fitness values. WBGA is suitable when the relative importance of the objective is known and can be represented as weights. It can handle the multiple conflicting objectives effectively but requires careful selection of weights to capture the trade-off accurately. Advantage of WBGA, it is simple and efficient. So the weight sum approach is easy to implement and can be efficient for certain types of multi-objective problems. Flexible, it allows easy adjustment of the relative importance of different objectives through weight assignments. Disadvantage of WBGA, it weight sensitivity. So the performance of WBGA happily depends on the choice of weights. Improperly chosen weights may lead to poor results, and it is not ideal for all problems. WBGA may struggle when there are complex nonlinear relationships between the objectives or when the Pareto fund is non-convex. You know what is non-convex. So this type Pareto fund is not convex. WBGA is useful approach when we have some prior knowledge of the relative importance of different objectives or can handle the trade-off between them effectively. Now, next one is that is niched Pareto genetic algorithm in PGA. So it is proposed by Horn et al. At 1993 and 1994. It uses a tournament selection scheme based on Pareto dominance. We'll discuss and Pareto dominance a lot in future class. Two individual randomly chosen are compared against a subset from the entire populations, typically around 10% of the populations, when both competitors are either dominated or non-dominated, when there is a tie. The result of the tournament is decided through fitness sharing in the objective domain. That is a technique called equivalence class sharing. Will use that is used in the case of NPGA. Advantage and disadvantage. This is easy to implement, efficient because does not apply Pareto ranking to the entire populations. We'll again discuss Pareto ranking in future classes. It seems to have a good overall performance. Besides requiring a sharing factor, it requires another parameter known as the tournament size. Sample applications, automatic derivation of qualitative description of complex objects that is given by Raspani 1999, feature selections and optimal well placement for groundwater containment monitoring, investigation of feasibility of full tank submarines. This is given by Thomas 1998. Now, in conclusion, what we can say that today we have learned some techniques that is known as VOES. We also know that WBGA and we have some introduction part of NPGA. So, right, the Pareto front will discuss. Pareto front will discuss and Pareto ranking will discuss in future classes. So today I am giving one question, try to solve it, I'll give some hint, you will solve it. So question for today's classes. Question is that minimize f1x equal to x minus 3 whole square, minimize f2x equal to something like you can write it x square minus 7, minimize f3x equal to minus of x minus 7 whole square, x belongs to 0 to 10, so you can write w1 equal to 0.4, w2 equal to 0.3, w3 equal to 0.3. So solve these things by the use of WBGA. Start with 5 populations. With 5 populations. So you can take the 5 population like x equal to 1, x equal to 2, x equal to 3, take x equal to 7, then take x equal to 9. So here fx will be 04 x minus 3 whole square plus 0.3 x square minus 7 plus 0.3 minus of x minus 7 whole square. So now single populations, now calculate fitness values, calculate fitness value, then do the selection, then do some crossover, can do the little bit mutations, then try to find the two more iterations. Okay, so this is the question for today's class. These are the references of this class. Thank you.